Great. Our first speaker now is Jeffrey Schenker, and he will speak about diffusion of wave packets in a Markov random potential.
Thank you
The
very
microphone
much.
switched on?
I think so, yes. I put a little switch in, yeah, okay. All right, thank you very much. It's a pleasure to be here at this wonderful institution. This has been a great workshop. I've learned a lot. It is, of course, not the 13th of August, but you know that anyway. Hopefully that's the only error here. So I'm going to be talking about some joint work with Yang Kang, who is currently at Michigan State University along with me, and this was recently posted on the archive. In fact, you can't get away with anything in this room. It was immediately recognized that this must have been posted yesterday. So I wouldn't have known that from the number, but that is a fact. So, all right. So here's the problem that is in the back of my mind. Despite the obvious fact that waves diffuse in a random environment, I mean, look outside and you see diffuse sunlight and things. And the very rich physical theory that surrounds that, we don't have a good mathematical understanding of this phenomenon in any sort of context. Okay. So now, of course, let's specialize. That was a very vague statement. So for instance, we would like to know that if we take this, the favorite equation of this conference, which is the Anderson model on the lattice. Did I manage to not leave my dimension on? Yeah, I didn't. I should have put d bigger than 3 somewhere here. So we take a wave function on a lattice, and d should be larger than 3. And we put a little random potential to modify this kinetic term. And we ask that the potential be small and random. And we want to know, do we see diffusive behavior in the large time limit? Now, of course, there is a result recently. Yeah, psi squared. Yeah, so I'm fortunately, the date was not the only error. Yes, absolutely. Of course, this is psi squared. It's amazing. I mean, you look at something. I mean, I went through this two times, and it's hard to see the errors. I should have had someone else look at it. There is a result by Erdős and Samhofer, which is a very nice result exactly on this problem. But they are forced to control the terms in the perturbation expansion to take both the disorder strength to 0 and the time to infinity. So this is lambda to 0 as t goes to infinity. And of course, when you do that, you have to rescale d appropriately by lambda squared so that you see something finite. And they get this result. But nobody has, as far as I know, a good idea how to control that without taking the disorder strength to 0. So intuitively, what's going on with this? And of course, maybe I don't have to explain this in this room, but let's just remind ourselves. Okay, a wave, we have multiple scattering. The scattering leads to a buildup of random phases. Buildup of random phases means a loss of coherence in the wave. Loss of coherence means that we can sort of begin to imagine that the wave's propagating without interference. And then we get something that looks like classical random scattering, which should go to diffusion by some sort of central limit theorem argument. I mean, I think that that's sort of the intuition behind the fact that this phenomena should be ubiquitous. But there are mathematical difficulties with every single step of that argument. Nothing there can really be done at a rigorous level. So now, of course, one major obstacle in a lot of these things is recurrence. If we start doing any perturbation expansion, the wave packet keeps coming back to where it's been before, and it keeps. So this makes it a little bit hard. It makes it harder to make the sort of loss of coherence precise, because you have to begin worrying about the effect of multiple scattering with the same object. And of course, that has physical effects too. I understand that. And it also makes it difficult to apply the central limit theorem, because even if you manage to get things as sums of random variables, they're not really independent random variables. They have some correlations. You keep coming back to things, and you have to control the recurrence. So let's get rid of the recurrence. Why don't we make the potential time dependent with short correlations? Now, this is a drastic step, but maybe we can obtain a model in which we can understand diffusion really mathematically at a rigorous level. Okay. Now, I should mention that I did manage to find some potential applications of such things. People have proposed looking at time-dependent problems to model signal propagation in optical fibers. So here's the reference to that. I came to this actually in an amusing way. Andy Green was a friend of mine while I was at Princeton, and we never discussed science. And at some point, I decided to look at his webpage. He's now at St. Andrews in Scotland, and see what he did. And I found this paper and said, wow, that really looks interesting. But we never talked about these things when we were both in Princeton. But I think, I mean, I'm not trying to claim that this is somehow very significant because of this portion of. Because of this. I think there's a more fundamental reason, which is that we need to have some rigorous mathematical model of wave diffusion. One idea I had going into this work was that, okay, I mean, let's try to prove diffusion in a time-dependent context, and then maybe you can approach the time-independent context through some perturbation around the time-dependent context. That, I think, has some sort of fundamental problems to it because doing this time dependence, as you'll see, we kill all of the localization. So I'll have traded sort of one difficult perturbation theory for another, that how am I going to see the localization arising out of this time-dependent problem that appears to be sort of a non-perturbative thing coming out of the time-dependent problem. So it's more or less clear that we should expect diffusion now, and only diffusion, because after all, we keep updating the system, and so we really don't have recurrence. So even in one dimension, we should see diffusion here. Can we prove it? So there has been some work on this. Of Chinnikov and Erickman in the 70s computed really the diffusion constant for, as far as I understand, I couldn't find this paper, of course, on the web because, I mean, in principle, this Soviet journal is translated, but I can't find, this is the reference I found, and then I can't actually find the paper. But from what I've read in other papers, what they did is compute the diffusion constant for a Gaussian white noise potential. And they see diffusion. But that's a very special situation. You can do a lot of things with Gaussians that you can't do with other variables. But that's still a very interesting result. Now, Pilet in the 80s considered some related things and proved some transients of the potential for some models that are related to what I'm going to consider here, and proved some bounds, and most importantly, proved an extremely useful formula, which you'll see below. And then Cheramenchantsev in the 90s considered precisely the models I'm about to define and proved diffusive scaling for things like the second moment of position, which I wrote down before, up to logarithmic corrections. And I should have added here, I recently learned of sort of very interesting work that Froelich and Deruck and Pizzo are doing on diffusion of a particle interacting with heat baths. Which really is, I think, very nice. OK, so what we're going to consider is a random potential that is generated by a Markov process. So let me remind you about what a Markov process is, at least loosely. We have a random path in some topological space. Usually you want it to be topological so that you can discuss something about the continuity properties of the path. And the distribution of some segment of the path past a certain time, given what you know about the path up to that time, depends only on the value at that time. So you don't need to know this whole history. You just need to know where the path was at omega of t. Of course, this isn't really a precise definition, but I think in this room, either you know how to compute with this, or you know how to define it, or maybe you know both. But OK, so when we understand that the precise definition involves sigma algebras and transition functions and can be a little bit wordy and complicated, but I don't think I need to put it up. The main point is that the process constantly starts afresh. And so this ultimately, although the proof doesn't go this way, this is going to get us around these recurrence problems. So these are absolutely the shortest time correlations that you could possibly have. There's no correlation from one moment to another, in a sense. No correlation of the increments, anyway. So let's take the potential that sits in the Schrodinger equation to be of the following form. Let's suppose we have some functions ux which map some Markov process in a topological space onto the lattice ZD, and we look at this time-dependent potential. So we consider the Schrodinger equation with this Markov random potential and some hopping terms. And in fact, we can let the hopping terms be fairly general. I will require that the second moment of the hopping terms is finite. This is probably a natural condition. At some point, I need to know that the Fourier transform of the function of the hopping of this guy, which is the symbol of this hopping operator, I need to know that that's a C2 function because I want to take its second derivative. That's what the nature of this is. And let's assume that the u's are bounded functions. That's probably not necessary, but it's convenient because it means we can skip over any questions about the existence of the dynamics. In fact, you can define the dynamics also with unbounded functions. I mean, you have to be a bit careful, right, if you have a time-dependent dynamics that you actually can make formal sense out of the Dyson series. And if these guys are unbounded, then to make sense out of it, I need to go to an interaction picture where I sort of integrate this piece exactly, and then you can make sense out of it, but it's just technically easier to say, let's suppose they're bounded. So what do we need to know about these functions and about the Markov process to prove diffusion? So I'm going to state some very general conditions which let us do it, but let's try and have a specific example in mind so that you can have something to think about. So this is the simplest example that I can come up with. So suppose that we have this topological space is all fields of plus minus 1 spins. So we have a function. Each element of the space is a function from the lattice to the set plus minus 1. Okay, and we'll just let the function u sub x be the nice bounded function, which is evaluation of this field at x. So it's the coordinate, the x coordinate of the spin. And let's suppose they just evolve in time in the simplest random way that one could think of, I think, which is that each coordinate, independently of all the other coordinates, flips its value at the times of a Poisson process. So this is a Markov process on this space. And does this actually satisfy my criteria that I should have a finite number of jumps in an interval? I'm not sure it does, so I should be careful about that. I wonder if I actually need that. What I say here, even if this doesn't quite satisfy the criteria, I can set up the proof of the statement that we get diffusion for this anyway. And so the hypotheses of the theorem hold, and what we have is the following result for which I should now explain. So we take the amplitude of the wave at time t. In fact, we take it at a large time, tau times t. We take the square amplitude, we average. So expectation here is averaging over all the disorder in this Markov process, and in fact over an initial distribution of the spins. And then we compute the Fourier transform of this expectation, of this mean square amplitude at x. We look at this expectation at wave vector k, and we scale k by 1 over the square root of tau. So this is diffusive scaling, because remember, if we're scaling momentum space by 1 over square root tau, that's like scaling position space by square root tau. And the assertion is that in the limit, as tau goes to infinity, this converges to the Fourier transform of the fundamental solution to a heat equation, which is this, a Gaussian. And that is diffusion. So we interpret this, so I'm sort of repeating myself here, that we interpret this as diffusion since it implies that if I take the x here should be zeta, if I take the mean square amplitude at zeta and I smear it out a little bit by some nice smooth function of position space, which I then, so r is a continuum variable here, and I rescale that diffusively, and of course I actually should have a tau to the d over 2 sitting out here so that I maintain the mass of this thing, then that converges to a solution to the heat equation in the sense of distributions. Yeah. Dimension plays absolutely no role in this problem because we've eliminated all the recurrence difficulties, so localization can't occur. The particle is eventually kicked out by this time-dependent potential. Okay. We also show that the mean square position converges to what you think it should. I mean, that doesn't quite at least by sort of softly follow from this, although it's closely related to that, because there's an implicit interchange in limits here. To get this, I want to differentiate this with respect to k, and it sure looks like I get that if I differentiate with respect to k, and I interchange formally with the tau tends to infinity limit, then that's what I get out of this. But so it doesn't quite follow from this that I have convergence of the mean square position. It's a slightly separate statement. But we do get that as well. OK, so this is the sort of result that we have. So let me now make a stronger statement about what, so let me state more generally what we need from our Markov process. We're going to ask that we have a stationary Markov process. So we want an invariant probability measure on some space, on the space where the process lives. The measure will be called mu. So for the flip model that I defined above, this is just the Bernoulli distribution on these spins, with probability 1/2 of being in one state for each spin to be in the one state or the other. So by Bernoulli, I mean, of course, a copy of Bernoulli for each spin, so a countable product of those. I want translation invariance. This was present in the flip model. So the functions generating the potential are actually translates of some fixed function u0 according to some representation of translations by ZD on the measure space L2 of omega by measure preserving maps. In the case of the spins, the flip model, this was just translation of the spins, and so I want this to be sitting there in this problem. Of course, this probably isn't necessary, but the techniques that I use are going to use it. If you had sort of translation invariance of bounds, you should probably get the same results, but that won't follow from these methods. OK, now we get a little bit more technical. The Markov process has a generator. So if I look at the expectation of some function of the Markov process at time t, given where the process was at time 0, then this defines, in fact, a strongly continuous contraction semigroup on L2 of omega, where L2 of omega is taken with this invariant measure mu. And as such, it has a generator. I mean, these are standard facts about Markov processes. So formally, ST is the exponential of some maximally dissipative operator. So the dissipative just means that the real part of the quadratic form is positive. Maximally means that it behaves sensibly and actually generates a semigroup. Well, that's sort of circular for what I'm saying there, but essentially that's what it means. So, and what we require is the following. We actually want a strict spectral gap away from so I sort of missed a comment here that if I take the generator and apply it to the function that's identically equal to 1, I of course get 0, because that's essentially applying it to the invariant measure, and that invariant measure does not move under the semigroup because it's an invariant measure. So 0 is in the spectrum of the generator. However, I don't want anything else near 0 to be in the spectrum of the generator. So I want the real part of the generator to be strictly positive once I go to the orthogonal complement of the vector 1, which is the space of mean 0 random variables. Okay? So, and I call this 1 over t because t is a time, and it's the characteristic time for the Markov process to return to equilibrium. Yes, L2 norm of f is 1. Otherwise, this can't possibly hold. Yes. In addition, I want this technical condition sectoriality. If you like, just take a reversible Markov process, so the imaginary part's 0. And that's already interesting, I think. But the point is we don't really need that. We just need to control the imaginary part. So for instance, you could have the Markov process could be a Brownian motion on a compact manifold with a drift. And the drift would be controlled by the real part, which was generating the diffusion. Okay. So, and let me just note that taken together, these two things imply that the Markov process converges to 1 exponentially fast. Okay. One does have to be a bit careful, of course, with these non-self-adjoint operators. I mean, this is absolutely clear if the imaginary part vanishes, because then you have a spectral theory for this, but you do have to be a bit careful in concluding such things for non-self-adjoint operators just from the existence of the spectral gap. But of course, it's well understood in the context of generators of semigroups exactly what conditions you need to get exponential convergence to equilibrium. And these are stronger than what you need for exponential convergence to equilibrium. And here's the theorem. So under the above assumptions, if for every x not equal to y, we have this technical condition, which I'll come back to, then we get diffusion. Okay? So exactly the same result. We have a diffusion matrix. It's positive definite. And we look at this. We get diffusion. Now, so what is this technical condition? This is, if you like, just think that the functions ux and uy are independent in the L2 space, so that ux of omega and uy of omega make independent random variables. And then, in fact, this becomes trivial to verify. But we don't actually need them to be independent. They just need to be. They just need to have sort of an absence of correlations, which this sort of thing is stating. Okay. First, let me notice, of course, the inverse of the generator is not well defined because it has eigenvalue 0. But we've stuck ourselves. We've picked a random variable which lives on the orthogonal complement of 1 because ux and uy are translates of the same fixed function by a measure-preserving map. So this has mean 0. So this is a well-defined object. And for the flip model, we don't need to verify this condition because now we have, in fact, the individual ux's in that context are mean 0. And you can always actually choose them to mean 0 because you can put the mean into the hopping term, as usual. And because they're independent in that context, the cross term in here drops out, and we actually get just twice whatever this number is, and it's some finite number. So we don't need, in fact, for the flip model, this is just the characteristic time of the Poisson process. Okay, so this, I mean, in many cases, this is not something you need to worry about verifying. It's just necessary to make the most general statement. So, going fast. Oh, I still have 11 slides to go, so I think maybe I'll. So let's talk about the proof. In fact, the nice thing about this is that the proof is extremely simple. So first, some sort of trivialities to get out of the way. We're interested in computing a quadratic quantity, the mean square amplitude. We have a linear equation. This begins to look complicated until we remember that the density matrix satisfies a linear equation. So we take psi times psi star at different points, and this satisfies a linear evolution, the whatever you call it, Louisville equation, where we use commutators with the generator to generate the motion. Okay, so the first term here is a commutator with the hopping term, and this is a commutator with the time-dependent random potential. So we look instead at the evolution of the density matrix, and then that's great because the diagonal elements of the density matrix are exactly the mean square position. So now we have a linear equation for the thing we're trying to compute. And here's Pilet's formula, which I call a Feynman-Katz formula, as did he. It tells us that if I take the expectation of so this is the mean value of the density matrix at some points x, y, that I can compute that as the matrix element of some generator, of some semigroup in some augmented Hilbert space. Okay? So I have here the Hilbert space L2 over ZD times omega, okay, which you can also think of as a tensor product of these three spaces. So ZD times omega is a measure space with an infinite measure on it, which is just a copy of the measure for omega on each point of ZD times ZD. And we're going to look at the Hilbert space over that. And then we have this generator that sits here. And the generator is just what I get by putting the Hamiltonian, the self-adjoint, the unitary evolution onto this space, now with a time-independent potential, and I add in the generator of the Markov process. So why is this a Feynman-Katz formula? I mean, in fact, usually when one looks at the Feynman-Katz formula, for instance, for Schrodinger semigroups, you are interested in relating this side of the equation to the expectation of some random process. Because over here, you put the Laplacian plus a potential, and you relate that to the expectation of some random process involving Brownian motion. In this case, we want to understand the expectation of the random process, and we're relating that to the matrix elements of a semigroup. So the sort of the perspective on the Feynman-Katz formula is sort of reversed here. That here's the thing we want to understand, and we're going to relate it to spectral theory of this object. OK. So is that more or less clear? I've put in some little definitions here. I'm going to call this guy K because it's somehow the kinetic term, and V, this is the potential term. Finally, rho naught is the initial density matrix. So I throw this thing up into probability into my augmented space by tensoring with the function which is identically 1. I evolve by this semigroup e to the minus TL, and then I project down onto the sites x, y, and the vector which is identically 1, which amounts to taking an expectation, because projection onto the random variable equal to 1 is an expectation. Okay. So this formula is going to be the basis of what we do. But we need to transform it a little bit. And there's a natural thing to do at this point, which is there's a group of translations. So if we translate our functions in our augmented Hilbert space, which depend upon points x, y in the lattice and some disorder parameter, then if we translate them simultaneously in all 3 coordinates, we make translations that commute with each term in the generator. So I wrote this out this way because I just wanted to make it clear that actually this, the main point is that the translations commute with the generator, but in fact they commute with each term of the generator. Okay. So you can calculate that. Of course, it should be that way because we set up the model to have translation invariance and distribution before, and this precisely encodes translation invariance distribution in this augmented space. So we should do a Fourier transform. I mean, if you have a group of translations, you should get rid of it, right? You should diagonalize with respect to it and do a block decomposition, block wave decomposition. So here's the Fourier transform, which we'll define, which is we take the wave function, we translate it by distance zeta, we multiply by the appropriate wave factor, e to the minus I k dot zeta, and then we evaluate this at some point. Now, I have to make a choice in defining this Fourier transform, because if I just have translation by zeta and x, y, and omega, I have too many variables. And so what I'll choose is to evaluate y at 0. So the x that sits here is somewhat different than the x that sits here in its meaning. The x that sits here is really the separation between the 2 points in my random density matrix that sits up there. So more explicitly, there shouldn't be an s zeta there. This should be gone. This is just psi. I was just sort of writing out the action of s zeta for you, which I don't really need to do because it's up there. Okay, and this should partially diagonalize L because this diagonalizes the translations. And so let's see that. Okay, so what we in fact have by this partial diagonalization is we have a block decomposition where we can now express the thing we're interested in computing as an integral over the torus. This is, which is where the wave vector in our Fourier transform lives. This e to the minus I k dot y gets us back to this position y. Remember, so we took the space zd times omega, and we transformed it by Fourier transform. So one of the factors of zd should turn into a torus. Here it sits here, and here's the other factor of zd, and there's omega left. So we now have this Hilbert space left. And remember that I told you that the spatial coordinate in the Fourier transform referred to the difference between the 2 coordinates in this position space representation. So that's what sits here as a delta function at x minus y, which tells us that this coordinate is this far from the second, is x minus y from the second coordinate. And now there's a generator and some initial object, which comes from our initial density matrix. What is the generator? Well, this you just have to compute. First of all, nothing happens to the Markov generator. The Markov generator is unaffected by this Fourier transform. The kinetic term now ends up mixing spatial and disorder space translations. So one piece of the kinetic term sort of stays the same, the one that came from translating the first coordinate, but we've removed the second coordinate from the picture, and translations in the second coordinate have now been transformed into mixed translations of the first coordinate and the disorder. Okay? And if you do the calculation, what you get is this. And of course, it depends upon the wave vector. We can't expect it to be independent of the wave vector. The potential transforms in a nice way, and this is the thing that you compute. So we end up multiplying by the potential variable at site x and subtracting the potential at the origin. And the fact that we get 0 here comes from the choice we made to evaluate something at the origin. We could have defined other Fourier transforms which involved evaluation at other points, and then we would have the other point appearing here, and the difference between x and that point appearing there. Okay. Finally, the initial value that sits here is just what you get if you compute this, which is just the Fourier transform of something that doesn't depend upon the disorder in this context. Okay. So now this is, in fact, the formula that we're going to use. So we have a relationship between the expected value of the density matrix and some integral over a torus of matrix elements of some semigroup. And now we need to analyze this semigroup. In particular, what we're going to do is we're going to look at the diffusively rescaled thing. So we divide the k by 1 over square root tau, and we multiply time by tau, where that's a large parameter. And what we see is that diffusion for this, remember diffusion was trying to get convergence out of this. Here we're only looking at very small wave vector. And so basically what we need to do is control the behavior of the semigroup for small k. It's natural, right? Diffusion is a long time, long space thing, so we should be looking at low modes. It's dominated by whatever's going on in the small modes. Okay, so let's see what we can do. So let's first of all look at k equals 0 and see what happens there. So the first observation is that L hat naught has an eigenvector, and it has an eigenvector with eigenvalue 0. And here's the eigenvector. So we know this, and it has to have this eigenvector because the density matrix has a trace that's conserved. Okay, and that's ultimately what this comes down to. So if you trace through where that's coming from, you get back to this. And of course, you can just immediately compute that this is an eigenvalue with eigenvalue 0, but this is why it's there. So in fact, if we multiply L hat naught by something that is independent of the disorder, all the terms drop out except for the one coming from the potential. So this is sort of an important point, and maybe I should go back to the definition of L hat k here. So notice or k hat k. Notice that when k equals 0, if I reduce this, if I average over omega, then this translation in space, translation of omega goes away, and this vanishes for a function that doesn't depend upon omega when k is equal to 0. So that's what's going on here. Okay, so that's what this is about, is that if I have a function and it doesn't depend upon the disorder, then the only thing that's left when L hat hits it is whatever is coming from the potential, which takes this thing which doesn't depend on disorder and puts some disorder dependence into it. And in particular, because the potential has mean 0, it's a difference of these two terms, when we now project this back down onto the space which doesn't depend upon disorder, we get 0. So this means that we have a block decomposition for L hat naught, which looks like this. It's 0 in the upper left-hand corner. It involves just the potential on the diagonal parts, and it's whatever it is in the lower right-hand corner, where the block decomposition is with respect to these spaces. H naught is the space of funny brackets with, yeah, obviously I put the brackets around the whole. Okay. This is the space that doesn't depend upon disorder. These are non-random functions, and this is the space of mean 0 functions, H hat naught, which lives down there. So this block decomposition will let us get a good picture of what's going on with L hat naught. So here it is again. Now the first thing to notice is that this block, of course, has a strictly positive real part. Okay? The kinetic and potential terms don't contribute to the real part because they come from the generation of some unitary dynamics. So the only thing that contributes to the real part is the Markov generator. And it has a real part which on this space is bounded below by 1 over t. That was our assumption, that we had this exponential return to equilibrium with timescale t. So now we do Feshbach or Schur or Crane, or I never know what to call this. It's the same thing with an inverse there, which should be there. So this guy is therefore invertible if I pick a complex number with real part less than 1 over t, so I don't have to worry about whether I can invert this block. The whole thing is invertible if and only if I can invert this object, which is the thing I get by reducing the resolvent to the upper block by the Feshbach map. Okay, and like I said, there should be an inverse here. Right? So, And usually there's another term here, but the block actually has 0 in it. So what I need to do is analyze this object. But now, look, this amounts to a simple estimation. We just need to see that the real part of gamma z is not too small, and we have everything we need to do that because we have the inverse of something which has real part that's not too small. And you need, I mean, in fact, I'm being a little bit brief here. This is why I assume sectoriality of the generator, because I want to make sure I have to that I can restrict my analysis to z in some compact region. I don't have to worry about z with large imaginary part and comparing it with this. Okay. But in principle, maybe you can go beyond that, but this seemed to be good enough for me. So the estimate we get, I mean, never mind, I mean, the details here, so I just, copied this out of the paper. The main point is that the real part of gamma of z is bounded by something. If z, notice, z has to be less than 1 over t for this to make sense. Real part of z has to be less than 1 over t for this to make sense. Here's some nonsense, and this is the thing, 1 minus the projection onto the eigenvalue for L hat naught. So of course that should be there because we should get 0 when we hit this, if we hit this with the eigenvector, then we shouldn't be able to invert things. But what this shows, in fact, is that even at 0, this is invertible as long as I stay away from this eigenvector, so it's a simple eigenvalue. Okay, so this really shows everything we want, and here's the lemma that we essentially proved on the last 2 slides. That the spectrum of L hat naught consists of 2 pieces. One is 0. The other is something I call sigma plus. 0 is a non-degenerate eigenvalue, and sigma plus is contained in some half-plane with strictly positive real part. Okay? And furthermore, you can check that because I put in the sectoriality to begin with, that we have the hypotheses to get exponential convergence of the semigroup once I project off of the eigenvector. So if I project away from this, I have exponential convergence to 0 with a mass that's almost this delta. Okay, so we're almost done now. Now remember, we don't really want L hat naught. We want L hat k for k very small. But I mean, for k very small, L hat k is not very far from L hat naught, and we've been handed the textbook situation for perturbation theory. We have an isolated non-degenerate eigenvalue. Okay, so for L hat k, if k is sufficiently small, then the spectrum consists of a non-degenerate eigenvalue, E of k, contained in some small disk around the origin. In fact, it has to have positive real part. The rest of the spectrum is contained in a half plane, which looks like this. Remember, if the norm, spectrum can move no further than the norm of the perturbation, so whatever the rest of the spectrum does, it's stuck in some half plane. And if k is sufficiently small, these 2 sets don't intersect one another. Furthermore, E of k is C2. Okay, this goes back to my assumption that the sum of zeta squared times the hopping terms was finite. It's 0 at 0. Well, that was the fact that we had a 0 eigenvalue for L hat 0. Its gradient is 0. That's a computation, but also something that has to be true. And it comes back to the fact that the hopping terms have only off-diagonal elements after we go, even if they had diagonal elements to begin with, once we went to this Liouville equation, because we took a commutator and we had translation invariance, the diagonal elements are all gone. Okay, so this gradient goes away. And finally, we can compute the second derivative using the standard formula from perturbation theory, which you should have to rederive because who remembers the sign and all those things. But in fact, in this case, you sort of know that the result has to be positive definite because you're looking at a semigroup. And so you can sort of guess the sign. And so here it is. We take the derivative of the kinetic term at 0. We hit it with the eigenvector. We take the inverse of L hat on the, of course, on the complementary subspace. But fortunately, we already got into the complementary subspace by hitting it with the derivative because of this off-diagonal thing that I just told you about. And then we project back down. If you do it carefully, you discover that when you compute this derivative, of course, you get this thing with one with the I, j on this side, and one with the j on this side and the I on the other. So that's why you get twice the real part. And now we're essentially done. Because if we go back here, we take the Fourier transform of the mean square amplitude. We write it in this form using our Feynman-Katz formula and the Fourier transform. We break this apart into 2 pieces. One is a projection down onto the eigenvalue for L hat k, which sits here. And the other is everything else, which actually is exponentially small in tau because of this gap condition. And then this here, we do a Taylor expansion of this around 0. The first two terms vanish. The second term is we've chosen precisely the right scaling. We get a 1 over square root tau squared, which gets canceled by this tau. So here it is. And everything else is a little o of 1 contribution as tau goes to infinity, because the next term has size 1 over square root tau. And in fact, we can, q of k converges to q naught to projection onto this guy when k goes to 0. Rho hat converges here. In fact, you have to do a little bit of an argument and do this for a subset of density matrices that have a little bit extra to k, and then use an approximation argument to get any density matrix. And then we have the result. Because if you go back through the formulas, you'll discover that this is what it has to be, which is the trace of rho naught. And so there's the diffusion matrix. It's the second derivative of this eigenvalue at 0. Well, 1/2 times that. OK. And that's the end of the proof. So, and I only have one more slide. I guess I've gone, well, no, it's about the right time. What condition upon sign up?
The sum of x squared, absolute value of sign naught of x squared.
That's only necessary if I want to derive the fact. So this holds for any initial condition. In fact, any trace class operator rho naught that you put in has this property. Okay. If you want to derive the fact that the mean square position scales like t, you better start off with the mean square position being finite. And that's the only place that comes in. So if you write out how does the mean square position depend upon time, it looks like the initial one plus something else, and that initial thing had better be finite, otherwise you have to stop there. So that's the only place that we use that. And it's not present in this because to get convergence to a solution of the heat equation, you don't need it. So for any initial wave vector, no matter how slowly, as long as it's L2, here's the answer. OK.
So this O of 1,
yes,
remainder, is not uniform in sign naught.
It's not uniform in psi naught. No. It is if I restrict the decay of psi naught. But as I indicated, that I'm cheating a little bit here, because if you check, rho hat naught k is not necessarily an L2 vector for every initial density matrix rho naught. So you actually have to go to a subspace which has enough decay to make this into an L2 vector. Then you prove this here. It's like Riemann-Lebesgue. And then you have an approximation argument which gives you everything else. Because, in fact, this thing, whatever it is, the difference between this for two different initial rows is always bounded by the trace norm of the difference. Because it's, you can sort of see that from this, because I have the sum, I have a trace, and this is just a complex number modulus 1. So I can restrict to anything that's dense in trace class and prove it there. And it's only if I restrict to some dense subset with some quantitative bound on the decay that I get something that's uniform here. Okay, so it's not uniform over all of the trace class. Okay, so let me just make some comments. So main point here is that diffusion in a time-dependent Markov potential can be seen in really an elementary fashion. I mean, this is not. If I didn't insist on proving something really general for Markov processes and just did the flip process, then you could explain this to undergraduates, I think. If you might want something sort of quantitative, and I didn't put in a disorder strength here because it doesn't play any role in the estimates, which is actually the abstract in the program is from a previous version where we did require small disorder, but I realized last weekend that I didn't need that in the estimates at all. But if you put it in there, you might want to see how does the diffusion constant scale as disorder strength goes to 0, and of course it looks like 1 over lambda squared times something plus something that's O of lambda. So Q of lambda is this is supposed to be an exact statement. I could have put equality here. So Q of lambda should be something that remains finite as lambda goes to 0. D naught is well behaved if the time scale of the Markov process goes to infinity, and it in fact produces, of course, exactly what you would get out of sort of a first theory of diffusion for a particle in a random potential. But notice this worked in any dimension, so some monster is lurking in this term, which overwhelms everything if we try to interchange limits. So of course, the statement that D naught is well behaved in the limit t goes to infinity is implicitly a statement that says take lambda to 0 and then t to infinity. And if I try to keep lambda fixed and t to infinity, oof, that's not going to work very well because of this term. Okay? And it shouldn't, because there's localization lurking at the band edges, and if you're in one dimension, it's lurking everywhere. So this term has all of that sitting in it if we try to take the t to infinity limit. I mean, I think one could prove a soft result that says that if you fix lambda and take t to infinity before taking the diffusive limit, then you converge exactly to the things from the random Schrodinger operator. But that is useless because the limits of the order of limits is all wrong there. If you could somehow take the diffusive limit first and then, anyway. Here's just the comment that we also get this. I already said that comment on an earlier slide, but and of course for that we need the mean square position to be finite to begin with. And so let me just comment then that of course the Feynman-Katz formula and the augmented space setup work for the Anderson model without a problem, but there's no Markov generator present. So if you go back and you take my formulas and you erase the Markov generator, the ones that are identities about expectation of matrix elements of the density matrix are true. But as far as I can tell, they're at the moment useless because we don't have this spectral gap, and it's somewhat difficult to figure out what's happening to what the spectrum of that operator looks like. And it's a big puzzle to me, actually, how, for instance, I could see localization in this augmented space formalism. So if I go to really large disorder, somehow I should be able to see what's going on, and I can't see it in this formalism, even though I know how to get it from elsewhere. Okay. But still, I sort of have a hope that maybe there's some way to do a perturbative analysis around something like these augmented space models and head to the thing we'd really like to see. All right, thank you very much.
As a comment, so you said at the beginning that there's related work in the physics literature that was motivated by thinking about propagation along optical fibers.
Mm-hmm.
So there's also related work that comes from thinking about multi-layer quantum Hall system with edge states at the surface and scattering between those edge states. And the basic point is that because motion along an edge state is chiral, then you suppress processes in which you revisit the random potential at the same point, and so you get back to the same kind of problem. So the result there is that if you, for instance, calculate the diffusion propagator, which you would normally do as an approximation by summing ladders, then for this kind of problem, the ladder sum turns out to be exact.
I see. Okay.
And there are also results on the nonlinear sigma model by Archer.
Oh, okay. Thank you.
That's without time dependence, but it leads to similar problems. Unit?
So you compute the square, the absolute value square of the solution of that equation, yes?
Yes.
Exactly. But since it is expectation, there should be some self-averaging quantity whose limit, thermodynamic limit, is your quantity. What is it?
I'm not sure, but I agree that there should be an almost sure statement that goes hand in hand with this. And but I don't.
Then I'll tell a bit more. I don't believe that it exists.
You don't believe it exists? Okay. Well.
But just second moment, and this is all.
So you think it's just a statement in second moment, but there's nothing almost certain. Well, maybe. I don't know.
And in fact, the very fact that you use the moments. So what is going on? You have a linear system with Markov coefficients. You can always write this as a second order system, first order system, just multiplying the equation. Yeah. So the general question about the moments of linear dynamical system is Markov coefficients. I believe it's known since long time in Markov theory of Markov processes. And it is known that you get the system of equations that are always soluble because they are back. They are triangular back. So the first moment via itself, the second via first and itself, etc. Therefore, this Feynman-Katz is more or less known factor. I think that is somewhere in book by Dinkin should be written. I believe. I don't know, but
Okay, so my attribution to Pillay may not be the correct one there.
I have a small comment and also a question about this. Well, adding to Untitled, I was surprised because there's a huge field, I think, $1 billion industry that calls diffuse wave spectroscopy, and it's basically what you have this problem. A lot of medical physicists and radiologists work on it. But there, the problem is also the phase. Can you say in your problem, is there absolutely no memory for phase? Because it was one of your issues you aroused for the stationary case that you have coherence. But is that you have absolutely zero coherence in time, or you have a finite coherence time?
Well, I don't think it's absolutely zero coherence in time. I mean,
But how long
because
is
these
this
are all
phase
log
coherence?
time limit results here. So, but I think I'm not sure. I'd have to understand that question. I don't
No,
quite
so
Can you
understand.
tell
there
anything
is
about the
exponential
expectation?
correlations. Since he has a gap, that correlation function exponentially decay. This is what you're asking?
It's about the phase, not the amplitude. But is there also
Which
correlation
phase?
Face away
Of
from
the
with phase
solution.
of wave function?
The equation is real. It is not Schrödinger.
No, it's Schrödinger.
Okay.
But then time depends.
The phase is not.
I'm not sure. I mean, since we go to the density matrix, I'm not sure we see the phase actually because it's diagonal. It's only in the off-diagonal elements.
No.
They all go to zero, and they go there exponentially fast, I believe. So that's,
Comments about the Markov approach as well.
So I wanted to ask one thing. You consider the density matrix, but I can imagine considering a higher order object. Maybe you can think of observing the wave function at 2 points and then multiplying with the complex conjugate to other points. You might call it a two-particle density.
yeah.
And it would be very natural in a many-body context, so interacting bosons,
Yeah.
fermions. But we don't even have to go that far. We already, with particle of non-boson or non-fermion statistics, you can consider higher order versions of the density matrix. So surely you could imagine asking the question that you addressed for the standard density matrix for the two-particle or n-particle density. And if there's diffusion, I would have thought that there should be some factorization property. So the question is, have you
see
considered this? I mean, you
I
might want
haven't-
to try to prove some factorization of correlations.
I haven't considered that. I mean, it's clear we could set up. There'd be some Feynman-Katz representation you could set up. That would be no problem. I would just have to check that we somehow didn't introduce extra zero modes, which I don't think you would. So I think something like that.
Because I think that would go at least some way towards answering Leonid Pasteur's objection.
Yeah.
Just, this going to higher order correlations is one way. And you don't go all the way to a statement that something is sure,
Right.
and probably almost certainly true, but
Right.
at least you cover some some way in that direction. You make some progress.
Yeah. That's nice.
Just going beyond the statement which is true on average.
Yeah.
Any more questions? If not, we have our afternoon tea break, and I ask everybody to come back for the final seminar of the day at 3:30.